Imagine you toss a ball straight up into the air. How high will it go? How long will it stay in the air? And just before it falls back, how fast is it moving? These aren't just guesses, we can predict them precisely. All thanks to the kinematic equations, a set of simple but powerful tools that describe motion under uniform acceleration with clarity, confidence, and precision. Let's now uncover the power of the kinematic equations, starting with a velocity-time graph. When acceleration is constant, the vt graph forms a straight line. We define initial velocity as u, final velocity as v, acceleration as a, and time as t. First equation, from the slope of the graph, final velocity v equals initial velocity u plus acceleration a multiplied by time t. Second equation, from the area under the vt graph. This area represents displacement. It forms a trapezium. Displacement s equals u times t plus 1/2 times a times t squared. Third equation, eliminate time from the above. V squared equals u squared plus 2 times a times s. These three equations are the core tools for solving motion under constant acceleration. Simple, visual, and powerful. Let's now derive the kinematic equations using calculus, a powerful and elegant method. We begin with the definition of acceleration. A equals dv divided by dt, which means acceleration is the rate of change of velocity with respect to time. Integrating both sides, the integral of dv equals the integral of a with respect to t. Solving this, we get v equals u plus a multiplied by t, where u is the initial velocity. Now we know that velocity is also v equals dx divided by dt, the rate of change of displacement with respect to time. Substitute our earlier expression for v. Dx equals quantity u plus at multiplied by dt. Now integrate both sides. The integral of dx equals the integral of quantity u plus at with respect to t. Solving this gives us the second kinematic equation. X equals u multiplied by t plus 1/2 times a times t squared. Finally, to eliminate time and get a third relationship, we combine the expressions and derive. V squared equals u squared plus 2 times a times the quantity x minus x naught. This is our third equation of motion, showing that all three kinematic equations, v equals u plus at, x equals ut plus 1/2 at squared, and v squared equals u squared plus 2a times x minus x naught, are consistent when derived through calculus. It's a great demonstration of how physics and math work together in harmony. Let's now apply one of the kinematic equations to a classic example, vertical motion. Suppose a ball is thrown upward with an initial velocity. Final velocity v is 0. Initial velocity u is 20 meters per second. Acceleration a is negative 9.8 meters per second square. Plugging into the equation v squared equals u squared plus 2as, we get 0 equals 400 minus 19.6 times s. Solving gives s equals 20.4 meters. So, the ball rises to a maximum height of 20.4 meters before reversing direction and falling back down. Let's now look at freefall, where an object starts from rest and falls under gravity alone. Here's what we know. Initial velocity u is 0, since the object starts from rest. Acceleration a equals negative 9.8 meters per second squared. Time t is 3 seconds, so we use the equation s equals u times t plus 1/2 times a times t squared. That becomes s equals 0 plus 1/2 multiplied by 9.8 multiplied by 3 squared, which is 1/2 times 9.8 times 9. That gives s equals 44.1 meters. So in just 3 seconds of freefall, the object drops 44.1 meters under gravity. Let's explore a fascinating observation made by Galileo. In equal intervals of time, the distances an object falls under gravity follow a pattern, an odd number sequence. Let's break it into 1-second intervals using the equation. We use the formula s equals 1/2 times g times t squared. At 1 second, that gives 4.9 meters. At 2 seconds, it's 19.6 meters. At 3 seconds, 44.1 meters. The distances during each second become, now, calculate the distance fallen during each second. The distances during each second become 4.9, then 14.7, then 24.5. And those follow the odd number pattern, 1, 3, 5. That's the beauty of Galileo's law of odd numbers. Motion unfolds with hidden mathematical elegance. Let's see how physics helps us understand real-life safety by calculating the stopping distance of a car. Suppose a car is moving with an initial speed. The car's initial speed, u, is 20 meters per second. It decelerates at -5 meters per second squared. We use the kinematic equation. V squared equals u squared plus 2as. Since the final velocity v is 0 when the car stops, we have 0 equals 400 minus 10 times s. That gives us s equals 400 divided by 10, which is 40 meters. So, the car needs 40 meters to come to a complete stop, a distance that could be the difference between safety and danger on the road. Let's not forget a crucial real-world factor, reaction time. Before the brakes are even applied, the car continues moving. Let's say the reaction time, t, equals 0.5 seconds, and the speed, u, equals 20 meters per second. Using the equation s equals u times t, we get, which is 20 multiplied by 0.5. That gives 10 meters traveled before braking begins. Now add this to the braking distance. The driver's reaction time is 0.5 seconds. At a speed of 20 meters per second, the car covers. Then, the braking distance, calculated earlier, is 40 meters. So in total, the car requires 50 meters to come to a complete stop. This shows just how vital both physics and human reflexes are to road safety. Before we wrap up, let's quickly recap the 3 golden equations of uniformly accelerated motion. Final velocity v equals initial velocity u plus acceleration a multiplied by time t. Displacement s equals u times t plus 1/2 times a times t squared. V squared equals u squared plus 2 times a times s. We derived these equations using graphs and calculus, and applied them to vertical motion, free fall, Galileo's law of odd numbers, braking and stopping distances, and even human reaction time. In the next video, we'll dive into the fascinating world of relative motion, where movement is not just absolute, but depends on the observer. Ever wondered how a person walking inside a moving train appears to someone standing on the platform? Get ready. We're about to explore motion from a whole new point of view.